Hello, everybody. Can you hear me? Okay, thank you. Good morning. Uh, Bear me a moment because I think we have some security upgrade. So the system let me have a two-factor authorization to log it in, which is longer than I expected. Yeah. Hi, Ancheng. You there?
Hi, Jun. Good morning.
Okay, thank you. As usual, please help us maintain the session. Yeah, you have raised your hand. Okay, fine. I got to my canvas. Make co-host of you. Yes.
Okay, thank you.
Well, yeah. Is the recording going on? Yeah, good. So yeah, Ancheng, please help us to have a look at the recording. And if I have some internet interruption or stuff like that, please help maintain the session. Okay.
Okay, no problem.
Thank you everyone for coming so early. I know that it's an effort. Thank you very much. So let's start our session today. Okay, our number is keep growing. Give it for a while. So in the meanwhile, you can take the opportunity to ask me questions. So maybe this is a good opportunity to have a small chat for a few minutes. Moving that. Okay. Okay. This is my video. I'm going to share my screen. Desktop too. Yeah, looks right. Okay. Okay, I have a question about the assignment. Uh, we will talk about the assignment in details in the next lecture. You will see that I will make an announcement today. We, as long as you can follow us along with our discussion about how those algorithms works, you do not need to worry too much about the programming side. You have a few sources for help. First one, you may notice in our Canvas site and in the modules, I zoom that in a little bit so you can see that, oh dear, because the UI design make it disappeared. It's here in the modules. And in each of the from the second one on, so this is module one. Module one is all about our theory. And from the second module, this is module two. I think I have published module three. You will find there is a tutorial page in each of the module. It looks a small page, innocuously small one, but if you click in, it contains a length of video lectures. So in each of the page, it will collect about 2 hours or 2.5 hours of the lectures. That guides you from scratch, from start to the finish, how to implement an algorithm, and it also contains the details of the derivation of the techniques we discussed in the class. So if you need help to implement those algorithms, you are very welcome to check out those video lectures. This is for one thing. Second, If you still have issues with implementation, there are rich contents online. I think I can recommend you some of the good video lectures later in the discussion board. However, I have to say many of those are focused on discussing the algorithms and models rather than the implementation. And when it comes to this implementation, many of the online tutorials are using the, the existing libraries, which is required not to in this subject. However, there is, let me think about that. You have, yeah, you have the example code, and you can take the third one is you can take the example code to our to my consultation hours. We have a couple of them. Wednesday, today, and Thursday, and we are very happy to help. So yeah, anyway, I will talk about the assignment in the next lecture. And also do not worry about reuse our sample codes. This is the duplication in code is not included in the plagiarism or repetition check. Good. I have James giving us an excellent question about the, I think the relationship of the perception coefficients and how the behavior of the model changes on the data space. Especially you mentioned that the curvy thing. That is a very good question, and I will cover that as our first point today. The notebooks from the, oh, I have another question about the notebooks from the video lectures. The short answer is I don't know. A little bit lengthy answer is they are effectively available because the simple code, the notebook that has been made available from this subject is based on what I have introduced in those video lectures, but that was done back to 2020. So I really cannot check where the original source code gone. You can use scikit-learn to pre-process, to prepare data, to organize the result, to evaluate. But for the core algorithm, those algorithms we have spent so much time to discuss in our class. We require students to implement from scratch. Okay, sorry guys. Now we are almost 10 minutes in the session. I said we will commit a specific time in the next lecture talking about assignment. So if you still have time, questions about assignment, please bear for a little while longer, and we will come to that point in the next week. Okay. Yes, you can reuse code. Okay. I'm finding my Zoom window. That's when you try to avoid the Zoom window, it's just everywhere. But when you try to locate it, it's just disappeared. Okay. Yes. Let's start. Okay, as usual, we begin the session by reviewing where we are, please let me remind you our roadmap. We will have we have already had 3 sessions out of our 10. Our plan is to do some theoretical discussion. It comes, yes. About machine learning in the first 2 lectures, and then we learn our first model in the 3rd and 4th lecture, and then we consider another family of the model, also some discussion about the technique, some discussion about the theory. And then we reconsider the machine learning from the perspective of evaluation, the how it differs essentially in the training and test stage. So this kind of stuff. And then we consider some advanced models, ensemble models, neural networks, and so on. So this is our plan. We have already reached this step. In the first lecture, we consider what is machine learning, and we have said it is software 2.0. And when you can apply it, when it's a reasonable a choice, 3 conditions. You have data, so that correspond to the experience from which the machine is going to learn. Second, you have reasonably belief that there is some trend in the data you can learn from. So the trend to learn. And the third, no math. If you have the explicit math or physical description of what you want to model, please just program it by yourself. Do not rely on some indirect mechanism. In the second lecture, we discussed the elements in the above mentioned a task or mission. So of course we have data, no out of business. And we specifically consider a particular kind of task which is supervised learning in this subject. We have some part of the data that is always available. We have some part of the data we want to predict, but for which we have knowledge in the training stage, not in the test. And then remember this little irregular drawing. So this represents the abstract concept that, okay, here we need to sit down, put every possibility on table. And from then on, we will focus on our table. We don't look away into other possibilities. So the hypothesis possibilities is a limiting factor in which we will search for the hypothesis about how to predict Y from X. Each member in this space is a map from X to Y. Okay. And if you recall that, I did the silly thing in the second lecture by manually do the selection using an Excel spreadsheet. So an algorithm, a selector within this space, and the loss, which is the criteria according to which you do the selection. So this is the second one. The third one is the last lecture. We consider our first realization of the framework. And for that, we have considered a particular format of the model, which is a perception. A perception takes the inductive bias. The inductive bias is another fancy name of we consider some possibilities but not others. So there so much so that we think we have some preoccupied by some idea. We call that a bias. It is not a bad thing. It does not bear the negative meaning when we talk about the term bias. So the inductive bias of perception is that for whatever observable information in the data, we summarize everything in one number by taking the summation of the weighted variables. By variables, I mean those attributes that can be observed when it is in the context of talking about the computation in the model, the derivation in some piece of math. We usually call attributes variables because now everything is a variable in the math. Those attributes are independent variables and the prediction is dependent variable, okay? So we take the weighted sum of those input variables and then we have one number. The bias is biased in the sense that we think this simply constructed number contains all the information we care about, we will ever think is interesting of all of this data sample. So it's summarized into one number. And then we do something about this number. We can do a lot of things about the number. For one example, we can do nothing about the number and just output that. That will be a linear regression model. And for the particular model we introduced in the last week, we consider doing a decision making out of the number. We can do positive prediction and the negative prediction. So that is achieved by a very simple rule. Consider this is the axis of your A value. We take some threshold here, call that B. Okay, and for everything that's below this threshold, we output negative. For everything above this threshold, we output positive. Okay, and so if you put that in a function form, you will see this called step function. Okay, to understand that, we need to link the so-called step functions input as the output of summarizing information from the input data. So, and this is the construction model. We left the last lecture, we left the last one at the point we decided it is an important question to address about how to choose a particular good set of W for the model. Okay, that is the question we have left from the last session and which we will address in this one. Okay, so are we good to go? I have a question. Can you reduce the inductive bias through some techniques? Well, no. The inductive bias is it's fundamental. It's a fundamental idea we do learning at all. The inductive bias refers to the fact that you need to consider the solution within a family of possibilities. You just cannot consider anywhere, everywhere, come up with any idea about the data. You do not measure the level of, well, this is, there is not a short answer about whether you can measure the inductive bias, because that concept is more at the philosophical level rather than the technical level. I give you a counter example of what it is in the lack of inductive bias. If you recall, I'm not sure if I can bring up that quickly enough. I think it's in W3. I do not remember it is in W3 or W4. No. Well, because this is not belong to this lecture, so I need some time to find it. But I just remind you, if you please remind yourself in this case, the example we use of the flowers, classifying the flowers, we have some colors here, we have some colors here, okay? And we want to build a model. By building a model, which means we want some definition of a behavior of something, but whatever definition you are looking at, the final result of applying what we want to learn on the data space on X will be a map of colors on the space, right? You can have a map of colors like this way, which looks right, okay? Alternatively, you can also map it in this way. Do you remember I had a very chaotic looking hypothesis in the previous lectures? Sorry, I got a query that you cannot see my screen. Is that true? Is my desktop visible?
Yes, it is.
Okay. Hi, please. Okay, it might be on your side. Okay. So if you remember those chaotic arrangement of the color, it is chaotic but consistent with data. If I put the data into like this. So you can imagine this is a possibility that although I make the colors crazily mixed up, but however, I can keep it consistent with whatever I have observed. This is a possibility, and this possibility is what we want to throw away using inductive bias. We want things in a simple order. Okay, that is one of the fundamental mind frame when people perform cognitive tasks. Okay, do not try to link. I have to remind you, do not try to link the simplification of things in technical term with what we talk about similar stuff in social science. We try to apply the same principle, such as to judge people rather than individually, but according to their, some other attribute. That is probably very wrong. What I'm talking about is we build classifiers technically. That must be reminded, please. So, but I think we try to mimic the intelligence of people by introducing this kind of principle. And also there is a very interesting, I think, argument and discussion about the factor of the cognitive bias and whether what is or whether possible to learn from experience. I think this argument starts from Aristotle and Plato back to maybe 2000 years ago in ancient Greek. If you remember, there is a anyway, I do not just dodge into onto this topic for too long. So yeah, let's assume that we have adopted. We will summarize everything of a data sample into one number. This guy. And the next question is to decide those guy, which is how to philosophy lecture during StillX. I need to keep away from the chatboard. You guys distracting me. Okay, so today's goal, we achieve this goal through 3 steps. Okay, we have 3 take-home points today. 1, a geometric point of view, a geometric perspective of this problem. 2, from the geometric point of view, we will have a very intuitive analysis about how errors happen. And from how errors happen, we then have a very intuitive derivation of how to choose, or in this case, how to change an existing W. So to eliminate the errors, to reduce the errors. So that is our plan. Here let's address 10,000 feet view question here. You might ask why we study errors. Why don't we just discuss when things work perfectly, when things look better, rather than focus on the errors? Why do you take this negative point of view? Okay, sure. Imagine that we feel this. There's no errors to look at. Then happy, we done with no errors to look at. This is a stop condition of the algorithm. So put it first. When there's no errors, mission accomplished. We have finished training the model. Okay. So therefore, when consider training, we consider how to reduce errors. So let's go to the first one. Actually, the first one is this viewpoint is what I mostly like everybody to take home from today. Once this is established, once we have acquired the geometric point of view, the next 2 points follows very naturally. You will have very intuitive understand of how these things happen, and then you do not worry at all. Also, the geometric viewpoint is a powerful tool in the machine learning study and research and engineer. So this is not only a specific piece of technique. This is a way of understand the questions and the models. So keep that in mind. Okay. Let me remind us one thing. Consider our little tiny model. You have x1 and x2 here. And remember, our viewpoint is consider x1. The value of x1 is the coordinate along one axis, and the value of x2 is the coordinate of another axis. And with these two coordinates, we can locate some position in a two-dimensional space. Okay. And now I will invite you to do maybe a couple of things. I won't number them. First one, consider maybe consider the origin of the space and try to imagine with the tail at the origin and point an arrow to the location where we have just decided. This is for one thing. Secondly, remember that we have a corresponding coefficient for each of the input variable. There is a very convenient coincidence here. So if you have one x, you will have a corresponding one w. You have the second x, you have the second corresponding w2. So, however many, whatever the number of x we are looking at, we will always have the same number of w accompanying those x. And therefore, by the same thought that we put our x in the space, we can put our coefficients, well, the collection of all the coefficients, if you consider we collect all the w in one object, we can put that in the somewhere in the space as well. Right? Now you can consider the coefficient also located in the same data space. There is a little caveat. There is a little issue we want to mention here. This is not the whole picture. For the whole picture, you remember after that, after we have the A, and in the perception, we have that, you compare A with some threshold B, and then do decision about that. Compare A with B is equal to compare A minus B with 0, right? So if you put this minus B graphically, it is like a minus B here. This guy is also a model parameter. So you may think, hey, Jun, if I take your geometric point of view, where do I put my parameter, this parameter in the picture? Okay, I quickly explain that, but if you cannot follow, it's okay. You can just accept. I can put my parameters, my model coefficients, everything, every number that affect how the model behaves. I can do this. I can put them in the same space as the data. I can do this. You accept that. So a little explanation. We take a maybe, well, I won't say that it's clever, but just it's a manipulation of this stuff. We link x0 here. I'd rather don't give it a number. I just call that something here. This, we imagine that belongs to the x part. That is a number with each data. And I call that 1. And not call that, I make it 1 for every data point. It is like, if you remember our previous imagination, you have x1 and x2 here. And x1 and x2 is from, like when previously, you have a data table, x1, x2, and the table is flipping 90 degrees becomes this way. So here is x1, here is x2, and the samples just line up to get into the model. That is the image we introduced last lecture. And by adding 1 to each sample, it is like add 1 column in the table and put every element in the column as 1. So when you flip the table, not flip, when you rotate the table 90 degrees, those 1 becomes here. It will join the computation from here, and then you add another x here. You call that maybe x0. But the name really doesn't matter from your understanding of the underlying stuff. So we call that just a dummy thing. Because it's not real, it does not contain any information, and nobody really implement this in the real computation. It is a tool to understand the thing. So with that, with one extension of the X space, now we are able to put those minus b as just as the coefficient linked to the dummy variable. You can call the W0. Okay. If you do not remember, if you don't follow the whole thing, please just remember the conclusion. We can put the model parameters, the model coefficients in the same space as we put the data samples. So that is the conclusion. Okay, so now we have put them in the same space. Are we good to go now? Let me redo the the coefficients are not averaged. I have some questions in the chat board. One question is the coefficient averaged? No, the coefficients are shared. You think you can think about the coefficients in the way that as something to regulate the information from the input. Those stuff takes in information from data, and those coefficients, they process the information. It is on the wire. It wires up the model, and then it is shared between all the data samples. It applies everywhere. Yeah. So another question, how can you denote X vector on the plan? To understand a vector, you need 2 points to define a vector, right? So we always put the other point at the origin of the plan. So maybe that plan, I have deliberately drawn that in this way, is not very generic. Well, if you consider a more a traditional way of drawing two-dimensional plans, you have maybe x1, x2. So when you have decided the origin is here, then you have something here. The corresponding vector is here. you have something here, the corresponding vector is here. Okay. Fine. Well, and let's go on. Now, with this arrow point of view, comes the very convenient. Well, comes to the technical point for today, and after get that point, all the argument follows becomes very convenient. If we write the vector as x1, x2, keep in mind, now I'm considering a particular vector. So maybe I can put a small index on the top of it to represent. That is not refers to the, like I'm not talking about height and weight of a person. I'm talking about something like the height is 1.7 meters and the weight is maybe 65 kilograms. I'm talking about a particular point. I'm not talking about the concept. Okay, so I won't use this very inconvenient denotation. I will just write x1 and x2. Maybe I use this a little bit curly writing to represent this is a lowercase x, represent sample. Not attribute itself. Okay, I hope that is more clear. So x1 and x2, let's call this is some x vector. I put a hat of arrow on top of that to represent the x vector, and w1, w2, the w vector. Those are two particular x and w's. Okay. Yeah, I go slowly. I also give you examples such as this is actually, this is our data table, x, capital X1, capital X2. So maybe this represent some particular X1, X2, 3. So this is X vector 3. So, okay. Then the computation of perception is x1 times w1 and x2 times w2. This computation, if you write it down in this way, you take all the variables or data attributes in one sample and takes the weighted sum with the corresponding W. This thing, notice that this applies generally, not limited to two-dimensional case. It's not limited to this simple toy example. This is a powerful tool that can handle, maybe you have maybe hundreds or thousands of variables. This also apply. If you remember something in your linear algebra, this is called the inner product between x and w. And what is an inner product? Well, that comes to the convenience of the vector viewpoint. The inner product corresponding to first, you do what? First, you do a projection of one vector onto another. Okay, so this little thing represents a right angle. When you do projection, you do that. You drop the x at the right angle onto W. So, and the value of this inner product is linked to this kind of projection thing in this way. It will be the length of the projection times the length of W. So maybe the first thing comes to your mind is, wow, is this symmetric? Is this well-defined? Which means if I project X onto W, is the same thing as if I project my W onto X. Right? So that is a good question. And the answer is yes, they are. And they both equals to the length of W, the length of X, and times cosine . You can call that theta. I know I need to give you some reminder of this. Okay. Consider one thing. Keep this simple. Let's, for example, think the length of W is 2. The length of X is 2 as well. So just make things simple. And now let's consider the situation theta is 0. So in this case, what do you have? W and okay, and the projection is of course itself. So basically, now I can write W or X does not matter. We have this thing. Okay, and remind you, and please be reminded, cosine 0 is 1. Then consider another example. They are 90 degrees to each other. Then we drop here we have we do not have a projection of any length, right? And therefore, you have this thing. And remind yourself, this is 90 degrees. Okay. And another case. So I need to remind you, this is a sine thing. Okay, if we are in this situation, look, this little red thing projection here, I deliberately didn't put a mathematical symbol here because I realized that this will give me trouble. And now it is at the opposite direction of the W. Therefore, this should get a minus sign. This is a minus thing. And please recall, in this case, cosine, something that is greater than a half of pi and less than the pi, this thing is a minus. It's less than 0. I hope this a little bit lengthy explanation gives you a good, well, maybe intuition about the behavior of the inner product. So I got a question, what is the motivation? You will find that very soon. And I am going to demonstrate you how that affects the behavior of the model. Okay. Now, with this understanding of the inner product, look at the data space. Yeah. Okay. This is a visualizer. Oh, sorry. Let me open another one. Okay. Now please have a look. In this part, I have implemented one thing that is, please be reminded, in Python, you write x that is equivalent to take this from a data table, and that is equivalent to our x1. So bear with me. I will consistently confusing the x0 and x1 when discuss code with math. They simply taking different conventions. Okay, keep that in mind. Well, anyway, now this 0.5 is applied to x1, which is something, if you consider this 0.5, okay? And for W2, we do not have anything linked with the second column. So the current W points this way. Okay. Uh-oh. I just want to be able to draw somewhere without affecting your understanding. Okay, better. Now consider this W. And please try to imagine then in the entire data space, I'm trying to consider is the inner product of any x with this guy. So consider x here. The inner products remind us of this. Okay, we drop this x to this w. And we drop this x to this w. I'll address one comment from the chat box. No, this is the same model. I just write it down in a different way. They are with one model, you are free to code it in a lot of different ways. This is just one way to code it. Okay. We can explain the details of the implementation later if you stay with me in the consultation hour. So, okay, if we drop this w, this x here, we get, okay, the inner product at this point will be the length of this projection times the length of w. Okay? And I will invite you to consider, how about if I consider this green dot. So when we consider maybe I put the green dot here. When you consider its inner product of W, it will be the length of this projection times, well, the same thing, the length of W. Okay, and those question mark is the important factor when we consider the individual data points. When we consider something here, it will be this length. That is important. When we consider something, maybe here, it will be this rainbow length. That is important. Okay. So with that understanding, I then invite you to imagine one situation. If I consider this green dot here, and I consider the green dot here, is there any difference between I take the inner product of green dot 1 and take the inner product of green dot 2 with the same W? No, there is no difference. Because if you, I think we need to zoom this part a little bit. Here, so we consider this projection. We take this length times the length of W. And if you consider this, we still consider the same length times the length of W. Okay. Now please try to understand the color on the screen. The color is according to the value of the inner product at specific points in the data space with W. Okay, so if 2 points are of the same color, of course, sorry, because for clarity, I just didn't use too many scales in my color gradient. We have a limited number of colors, but try to imagine that the color changes continuously from this, from the left-hand side to the right-hand side. Try to imagine that. Okay, now imagine the points on the plane with the same color represent those points that take the inner product with the current W, result in the same number A on which we will make decisions. Because the decision making is a simple one, we try to understand how the model behaves by understand how the model produces A. Okay. I will strongly recommend you to log into the notebook and try out the code. Nothing is more comprehensive than you just get a hands-on experience on this. Now I'd like to change this W a little bit. I will move it from happily sitting on like from 0.0 to 0.5, a little bit up. Okay, maybe I will take another W here. How to do this? This is take the first column. By the way, if the text is too small on my screen, just let me know, but I think it should be okay. So this takes the second column, remember this? And if I maybe think about that, maybe put 0.2 here. Okay. Now, before I hit this, try to imagine what will happen here. Try to imagine this. Okay. Give you a few seconds to think about it before I hit it. And in the meanwhile, yes, I'm collecting the number of people who are following. That's good. We have a significant number of people who are following, and some people need a little bit of time to think about that. Okay, while you are voting on whether to go, well, I think the number is gradually look more optimistic. I will hit this. Right. Can we rotate it a little bit more? Yeah. For example, now I'm doing the new W. So now maybe a little bit smaller than 0.5, make it 0.3. And higher than 0.2, let me make 0.4. And then also imagine what will happen. Okay. So I hope you are getting the idea of the model's behavior on the data plan and the numbers of the coefficients. Good. Well, if you are looking at your screen, I cannot zoom that out too much using my screen. I don't know how to do that on the Zoom. But if you look closely, you will find the small numbers on the screen. It is like when you are reading a map. The parallel looking curves that represents the equi-height positions on the terrain. It's the same here. The little curves represent the terrain of our A values, and it's the same number line on the same line here, which is perpendicular on the right angle with our X. And the decision making is according to such a number. And because we have introduced, we just put a number B here, therefore we can make the decision between B and, make the decision just by comparing with 0. So I changed this B a little bit. Therefore, I think I increase the number a little bit. You will see, maybe minus 3.5 and see what happens. Look, now the 0 line is here. Okay, this is the 0 line. And look, This is the classification boundary of the perception. Okay. And from this understanding, you probably think, when W points to, when W points to this way, the decision boundary is this way. And of course, the two classes are distinguished along this direction. Then how about I rotate W to make it point that way? Okay. So I'm doing this. And here, let's make it minus 0.3. I think I need a pair of parentheses. Yeah, let's try, because I can just put it, make the arrow from this side to this side without changing its height, and just maybe have a try. And we adjust the values here. Now it's minus 3.5. So I probably make it a little bit greater. Oh, it's too large. 0 is here. So maybe, so. Okay, 0, just 0. Oh, now the boundary is here. Okay. Right? Things start looking on the brighter side. Maybe I just change this a little bit. Oh, I stopped playing this. I'm not very good at this. One more last time. Okay, better. Okay. With this, we are ready to derive, to analyze, because we okay. Now, this 1 hour 20 minutes into the session, we delivered our point 1. Geometric point of view. But fortunately, we have discussed. This is the important take-home point today. And the next 2 steps are very easy to understand given our understanding of the first point. Okay, so let's go. Well, consider our situation. We have a dichotomy to make. By dichotomy, I mean we have 2 ways to go, only 2 ways to go. If you have only 2 ways to go, you have only 2 situations to make errors. You should go this way, but you go that. You should go that way, but you go this. Okay. We write it down. Error analysis. Ground truth Y, positive, negative. current situation. Okay. Spelling. I remind you to make my drawing a little bit easier. In this argument, I will put the guy that is horizontally lying on the plane as X. So in the previous argument, that guy is W, but you know, it's the same. The situation doesn't change. It just makes the figures a little bit easier to draw. So when you want to produce positive result, and you know that you are making an error right now, so you must have some situation this way, right? And vice versa. If you put it in plain English, it's something like this. I should have been aligned with that X more. Okay, and this thought directly naturally gives goes to the think of then how to align with X more. Let me remind you the very nice operations between vectors. So you have vector 1, have vector 2. So vector 1 plus vector 2. What is this? How to compute that? Okay, I compute that for you graphically. Ooh. Okay. This is vector 1 plus vector 2. Has that inspired you something? I want to be more aligned with X. So I'd rather to just add X to myself. Written in a programming language way, okay. I copy. Oh. I paste. I put it here. Ah. I just have this. That's it. And on the other hand, when I want to produce a minus result, say, my W, where is my? Okay, I do not have the other let me deliberately make some errors for you. And say, because we know that in this case, I have chosen W to point this way, right? This is a W. And look, this represents this kind of thing. Oh dear, I think I have completely get look at this. I completely get the classification upside down. I should have flipped that. Well, yeah. Let me change that. So the yellow one should be downside. Okay, it's easy. We just flip the sign of W and flip everything. Okay, sure. Now we know our W points to this way, okay? And you can see that, where is our W? Okay. On this sample, it is living in the positive side of W. However, because we are analyzing errors, for that sample, the ground truth value is minus. So it should have been in this. We cannot move samples. We cannot move them. They are given. We can just change W somehow to bring that back. You cannot just move the line here, otherwise you will make every sample there disagree with you. So following the same argument here, I should have been aligning with that XMOL. That will become, I should have been aligning with a negative minus XMOL. So that will become. Okay, so you might realize that with this, we do not only analyze the error, we have already covered our third point, how to correct it. Look at our Python implementation. So this is a little bit formal implementation. Oh, in here, I put all the parameters, including W1, W2, and W0, not a good, very good order anyway, into the same parameter H. So the first two elements of H represent our W1 and W2. This guy represent this constant. And I have said that the geometric view also applies to the constant. We will see shortly. So the computation goes in this way. It just to in a collective way to compute for a data table. Now, because we are doing a computer software implementation, we consider not only individual X, we consider apply the W to every single row of X altogether. And this W, that is corresponding to the H parameter from the first until the second last. This one not included. So we take each row of W and multiply that with the leading elements in H, okay. And left this one. And after all that, we just plus the last element here. That is what I've said. You could have just attach a row of X, and then we can just then multiply with H. But this way, we will waste the memory here because this doesn't carry any information. Okay, so we just do the multiplication on this side, and this is to do this computation after the multiplication. So 1 W1 x2 1 W1 x1 2 W2 x2 2 W2. After the multiplication, we have a table, and that table that is called axis 0, axis 1, and we take the sum of this table. Okay, that's a computation of perception. And the prediction is made by doing the computation with the current parameter H and take the sign of it. Okay, now comes the training algorithm. Given data X and Y, we loop until we can't find errors. Okay? We use our model to predict, and then this is to find errors. This is to find the indexes where it makes errors. Here is an important reminder. The computation here is not about to considering all those training errors altogether. No, it's not like this way. We take one, and then we use this one to adjust our W. And then we recheck how things go. If there are still errors, we then take another one, so on and so forth. Look, here we take a decision making. We check if there is errors at all. If there isn't, we break out from the while loop. When there is errors, we take that one. Okay, then look for our h here, which means our model parameters. We increase it by x, the corresponding error making x, and which this is just a shortcut. We can do a if then statement. If the corresponding I would like to align with x, positive x, and we increase it by x. And if I would like to align with negative x, I increase with negative x. But in this way, why I just don't say, I would it have been aligned with x with the sign of the corresponding ground truth y. So this is just a shortcut of the if else statement. You can check that back at home, that when y is positive or negative, this increment is always consistent with our argument here. And this one, the last guy, is increased by, remember previously when I have just said, I just look at the boundary, okay, I need to increase you a little bit, I need to decrease you a little bit. Well, you can formalize that as, you can just increase it at the same direction as you increase or decrease x. However, remember our dummy variables. These are dummy ones. These are always 1. So you can actually see, I want 1 times this. Because for whatever sample I, this corresponding variable is always 1. You can put a 1. But of course, you do not need this. Okay, then that is our training algorithm. I'm bringing up the quizzes. And in the meanwhile, I want to know if everybody is following along. Okay, I'm opening the quiz. I made an announcement today, which will be available as usual time, but I want to put some points here to remind you. From the next week, we will assign quiz in 2 groups, into the postgraduate group and the undergraduate group. So everybody here will receive the quiz on time in the class, and the deadline is loose. You have 1 more day to complete that. The deadline is tomorrow. So you have plenty of time. However, I have to rely on the system to assign the quiz to each individual student. If someone have changed the session, or if the system has mistakenly do not put in you to a specific student group, you will not receive the quiz next week. In that case, don't panic. I am just trying to arrange the stuff as we stated in the subject online. If that does not work, we will manually change your grid. So we will manually reassign the quiz to you and change your grade accordingly. So do not panic if you do not receive the quiz next week. And if there are too many issues, we will just change back to the way we do that in this week. This is for the first thing. And the second one, okay, I'm happy to see everybody is following along here with the poll. You can see that. I think this style of going with everyone works quite well this semester, but I still want to learn from you to give us feedback about how the subject is going, on which direction you want us to improve. Therefore, please give us your feedback about the subject from the studentfeedback.utseduau, sfsutsedu.au. Please give us this feedback. Okay, thank you very much for this. It just takes you very few minutes. Now let's look at the quizzes. I have to say, I will trick you along the quizzes because I want to deliver some more points in the class. So the first quiz is a deceiving one. Consider a perception model F, which achieves the best overall performance. Let me put that first. This F, this hypothetical F, is not available and it will never be available. This is just a conceptual object. We think of this F. This F can achieve the best overall performance, which is a minimal error on the underlying data distribution. So which is the following statement is true. And this quiz, this some of the common misunderstanding of learning. And the correct answer is nothing is true. F could be something else than otherly stated. Okay, now actually you know that I want to deliver a message in those error, it is wrong answers. So let's still put some time in to look at them. Okay. One, F makes zero error on the training data set. No, that is not true. Sometimes it is impossible to achieve zero training errors or zero errors at all. Think about that. Okay. If the underlying condition is in this way. Okay. So you can argue somehow we could try to put the best performing perception here, because remember that we have to confine, we have to restrict, limit ourselves into some family, and this family in this case is the perception. So you need to cut a line. This is a hard call. It's not an easy call, but you need to cut the line. When you have that line cut, you are going to make errors. And we are talking about the best cut, but even in the best cut, there could be errors. So this is wrong. F is the perception that achieves the minimal number of errors on the training set. Well, that is truly deceiving. It is the best one. Why? It could be, how can it be the situation where this is not the best performing on the training data set? Okay, consider that way. Maybe the bad behavior is not on your F, but on the training data set. Recall our concept. The data in our data hypothesis algorithm and DHAL in this 4 element, that particular one is given in a black box. And we do not have direct information in the box, and we have to rely on the samples from the box. Okay. Then the samples may be misleading in some case. For example, in the same situation, how about if by purely bad luck, I had samples in this way? Is that possible? Yes, of course. This is completely consistent with the underlying distribution. And if we are removed from the oracle, from the omnipotent God view of the underlying distribution, now think about that. We end up with, I copy that. The viewpoint here, right? Without the God view, we only have this. So how you cut that? Usually you get something here to cut it. Okay, and maybe definitely, okay, sorry about that. I haven't put that correctly here. No, this example is not good. Let's think maybe. I have a lot of stuff here. Just to make the life more difficult for ourselves, which is ridiculous. So now you may have chosen this one. Okay, and definitely the previous what we have said, the optimal guy is worse off than this inferior guy. Look, if you apply this guy onto the underlying distribution, this is indeed worse than the optimal one. But, well, this is just not reflected by our data samples. So this is an unfortunate possibility we need to take into consideration when perform machine learning. Okay, this argument is a little bit mouthful to bite. So if there are perceptions that can achieve zero error on the training dataset, F must have zero error on the same training dataset. No. This refers to something maybe like this. See, we have this. Let's see, perhaps the best F is here, okay? But maybe we have samples in here and samples in here. This is also purely bad luck. And then if you look at the samples, of course, I will assume we all know that for our F, it classifies that part as green and that as red. If it classifies that side as green, all those are errors, right? So if it classifies that as green, so this side is considered as green by F and this is red, then F wrongly classifies this. If this happens to be in the training dataset, F makes errors in the training dataset. But consider another guy, the rainbow guy. The rainbow guy can achieve zero training error. So maybe this is stating from the other point of view that zero training error might not be a good thing. However, there is another statement I want to let you know, that is that if there is some perception that can achieve zero training error, then the training algorithm we have discussed, although it looks at one error at a time, it looks only one error and change its model parameters according to one error, not globally. But this iterative error by error correction scheme will achieve zero training errors if there is any perception that can achieve zero error. Then our algorithm will find one achieve zero error. Might not be the same one, but we will find one. The proof is in the recommended reading book. It's called Learning from Data, a short course. I think I can extract the proof and put it in the discussion. If you are interested in, you can have a look at that. I think I have also put the proof in the video lecture. Question 2. In one step, a perception is adjusting the parameters according to some data sample X. And it asks the behavior of the training algorithm. So the important part is that the behavior of the sample on the sample where it had made error will improve, because look at our motivation. We will adjust the model behavior according to what I should have done argument. Okay, so the model's behavior HXW will change towards the same direction of Y. It will increase if y is positive 1, and if y is negative 1, it will decrease. So this is the correct answer. And why this, of course, those unqualified statement of increase or decrease is wrong. And why this is wrong? For x prime, this is better understood by. So if the adjustment is according to this one, and it's asking for something like x prime here, what is the behavior of the model according to this x prime? Undefined. We haven't discussed about the behavior on x prime. It's not guaranteed. We cannot state anything about this. Okay. So it's choice. Question 3 asks a thing that combines our understanding in question 1 and question 2. Well, simply put, when you change, I give you the short description of what is E in, what is E out. E in means the training error, the errors that has been made on the training examples, and E out means the generalization error out of samples. Okay. If look at this, if you only look at the samples and consider where are correct classification and where are incorrect classification, well, then you are talking about E in. And if you look at the underlying scape, a landscape, underlying one, ground truth one, although you will never be able to directly access it, but you need to keep that in mind. Why? Because in future, after you have trained the model and delivered your model to your customer, they will receive samples from those unseen areas. Okay, so that the behavior on all the areas is called E out. So that is the understanding of E in and E out. But the point here is both E in and E out are global behavior of the module, model on the entire data collection or the data space. So the behavior is not well understood for a single step of training. Therefore, the correct answer is it is possible for both E in and E out to increase. Okay, summarize. Answer. F, the statement of F is wrong in all the other 3 statements. F could be something else. Second, the behavior of the hypothesis will change towards the same direction of Y on the particular X. It is not defined on other X prime. Third, both E in and E out can possibly go up. That's the answer. Okay, we are right on time today. A very tornado ramp up. We have studied 3 viewpoints, three takeaway points. We take a geometric viewpoint of the data space, and we put our weights as a virtual point in the data space, and then we transform the computation of perception, the weighted sum, as an inner product of 2 arrows, and then we can consider how the model's behavior by considering the alignment of 2 arrows. And then the the training
sorry.
becomes
Sorry, what was the
finding a direction to rotate the arrow of W so that it will cut the X according to the training data. And then we analyze the possibility of errors comes out. Basically, it means if you want to go this way, but the alignment in this way. And from the sum of vectors, we quickly derived a scheme of change our parameter so that
sorry,
the model's
what was the
behavior becomes better.
What was the justification for question 3? I'm just writing it down.
Okay, so basically that is what we have learned today. Remind you, please do the SFS, the early student feedback. And if you want to stay, I'm still here for half an hour. After this half an hour, we rearrange Ancheng's consultation hour. He will stay here for yet another an hour, but that will from a different Zoom session, which he will which you can find in the Canvas. So thank you very much and have a great day and a great weekend. Bye bye. If you want to stay, you stay. You do not need to just say bye bye. When you try to thank me, try to do the early student feedback. And if you have questions, you can put that in the chat box, or you can just speak up.
I just have a question.
I cannot hear you very clearly. Can you test your audio or bring yourself closer to your micro?
Hi, can you hear me?
No, is that me? Let me check.
So I could hear him clearly.
Yeah, good. Please.
Can you hear
Now
me? Okay. I was just going to ask because I'm writing this down. What was the justification for the question 3 answer? Because I don't quite understand.
What is the justification for?
I think that he wants to ask about. I think that he wants to ask about the explanation about the question number 3, right?
Number 3.
That's right. That's right, James.
This one, right? This one?
Yeah. Why does it have to? Why is it in the training step? But not after.
Let me show you. Okay. Look, because now we are in a more narrow pace, so I think I can take the luxury to demonstrate, because in the class, in the main session, we have some time arrangement I have to follow. But now I think we can see that more clearly. Look at the situation we are now having. Our model almost work nicely right now. Okay, but we have errors here. We have errors here. We have errors here. Okay. Let's try to adjust the W. Let's consider E in and consider E out later. Okay, so the E in is this. Wrong, 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 right? Okay, so we just need to find one thing that tempe is this.
So sorry to interrupt, but how do we find the errors? Like
I'm doing this.
Right.
I'm doing this. Look at that. And look at okay. So what we need to find is when this guy is greater than 0 and this guy is greater than 0, but they don't like each other. So smaller than. That means, look, I give you a short. This means and. Okay, so that means when our prediction is greater than 0, but our desired answer is less than 0. This is one kind of the error, right? The other kind of the error is, of course, this is less than 0, but that is greater than 0. But anyway, let me find one kind of error here. You have only one guy here. I think it's probably here. Okay, let me try. It will give you the index here. So 67. 67 is this bad guy. Okay? Because we want it to be less than 0. However, it is classified as greater than 0. Right? In this case, our W is this way. And W is greater than 0, but we want it to be less than 0, which means we are considering this guy. Okay, so with this, okay. Now, recall that the corresponding Y here, the Y here needs to be less than 0. So Y here is -1. I just put it here to remind ourselves. And I'm just doing that manually. Which I decompose the loop steps from the implementation below, and you can study at home. Now, our W is now 0.1. And the other one is okay. And let us put just here, and this is right. Let's run this and run this to be sure that they are just doing the same thing. Okay, with this, now I can try to update my W. You have a look at what do I mean by this, just the first until the second last element in W. Okay. That means this will be increased with this guy. Right? And this guy, the last one. This is until the last one. This is the last one. Okay. Show you the original and the adjusted W. So after the adjustment, just for comparison, okay, I take a photo of that, put it here. What should I do with that? Oh. Okay. Yes. Let's run this. You see, this definitely put this into the negative part, right? However, it has just throw everything here into the negative part as well. Okay. Which classification is better? This one and this one. Of course, this one, the original one, is better. This is much worse. However, we have just corrected the classification at this single point. Now this is no longer an error. Right? So that means in the new hypothesis, errors in the new hypothesis can be more than the errors in the old hypothesis. And you can understand by changing the behavior in such a way, if we have changed the behavior in such a way, it is very much worthwhile. And if you imagine that our underlying, if we have some underlying distribution in this way, this update also messed up with this underlying distribution. So, and that means both the E in and the E out, both, if we test it on the samples, or we test it on the underlying data distribution, both evaluation will get worse. I mean, both evaluation can get worse. Okay. The next question, where can I find the code? The code, I do not have a very good memory. Okay, it's just a week 4 in the Canvas site. It is here. This one. Okay. I'll show you again. It's here. Okay, any further questions?
Yeah, I was just wondering how you got the arrow in the graph that you have on screen, saying that that's the direction of W. Not the top one, the colored graph on the right side.
This guy.
On
Yeah.
your right side, like your screenshot. Yeah.
Yeah,
You know,
yeah.
you have an arrow of a.
Yeah,
Yeah,
you want to know where did I find the error? I need to remind you.
Not the error. The direction of W.
Yeah.
Yeah. How did you get that for that graph? Like how?
Okay. That arrow is imagine. I imagined that arrow. But if you want to, where did I get the number of the original W? I think that is your true question. You know, I have discussed. Well, you have the current W, and that is your situation, and you need to change it in this way. But to change something, you have to have something originally. Is that your question?
I was just like, so I know like you set the W, the weights as 0.1 and minus 0.4 as the original one.
Yeah.
But then I'm not sure like how you like drew that particular arrow in like the graph for that.
For that arrow, okay.
Yeah, like how
if
do
you that arrow is corresponding to this. That arrow part is simple. Where is it? Okay. This guy. If you think a coordinate system, okay, 0.1 and minus 0.4. Then you have something like this, right?
Yeah.
So that is where the error comes from. But you want to ask where these values come from. Then easy. It's from random.
Yeah.
That algorithm works from random values.
Okay, yeah, I got that one. Thank you. Yeah, I just was wondering the arrow. I think the graph that you drew right now cleared that up. Yeah, thank you.
By the way, Ancheng, before we go, you will still use the originally allocated at Tuesday link for today's consultation, right?
You can change the time arrangement or create
I know I
another
can
one.
change. What I
Okay.
mean is like we have a schedule here.
Yes.
And we decided that because very few people attend in
Thursdays
in
session.
this one, yeah.
Yes.
So we think we will move this one right after I leave, which means after 10 minutes, we will start this one. What I want to
No
ask is,
problem.
will you use the same link, the same Zoom link here?
Okay.
Okay, if you do this, I will just change the time here because we have already tell everybody in the class here. And I will also put that in the arrangement. I think I will just change it now. You do not need to change the number of the ID of the Zoom, right?
The Zoom is created by you. Do you remember?
I didn't remember. I preset that Zoom, and oh
Yes.
yes, and then you will be the co-host.
Yes. So you should change that.
Fridays. Okay. I have never been very comfortable with those PM 12 PM thing. I always put a midnight or noon thing. Okay. Sure. So
Hello, sir.
yeah.
I'm just wondering, when you were saying like next week's quiz, you were saying it will be divided in a group or something.
Yeah.
Can you repeat that?
Okay. Look, I actually can show you the arrangement. Modules. Basically, we have two groups of people, and according to our subject outline, the quiz should be in class. And currently, the Wednesday people have 3 days to do the quiz, and the Friday people have 1 day to do the quiz. It wasn't a problem previously, but just to be, more organized, I set it as the deadline to be 12 p.m. of the next day of the online session. So for this guy, it will end at Thursday, and for you guys, it will end at Saturday. And then I assign the quiz into two groups. So the groups, there is one group here, another group here. In theory, hopefully, every single student should belong to one of these groups. You must enroll in one of these subjects to get in, right? However, that group is set up by the CSS system, which sometimes can become inconsistent with your study plan, with the whatsoever. So I'm not very completely sure that there won't be problems, such as maybe we have some students who are in the subject which is successful, but isn't allocated in each of the group, and that will create problem for them. So I just give you a caveat. If that happens, don't worry. We expect some. Maybe there are some issues. If there is some issues, we will just go back to the current arrangement, which seems to be okay for everyone. And maybe it's probably a bad idea to fix something that hasn't been broken. So that's it. I got Ali ask Ossie, well, for that thing, if you successfully for the quiz 4 thing, if you successfully receive the grade on Saturday when the quiz has ended and I post the marks. If you have the marks, okay, then you do not need to do anything. If you accidentally, used up all your chances or something like that, then you let me know, because we just take the highest score of your attempt. You can do the second time, and if it works for you, then that's it. Okay, so
I think Hina has a question.
really,
Is Hina here?
Yes, I'm here because just now that girl asked a question. I'm not sure. She's asking the one that I am trying to ask. So I'm not sure. I just confused.
you mean you were confused, but you are now clear?
I am pretty clear now because just now it explained that
I'm
when
sure
she
that,
asked the question that
yeah. Okay. Actually, I thought Hina, you was that girl. I thought I was addressing your question there, but I didn't realize there are two different people ask the same question.
Yeah, but I'm fine now.
Okay.
Thanks.
Okay. Okay. Then we wrap up today. Thank you very much.
So one more question.
Okay.
I'm just wondering, like, what is the idea of training a perceptron?
Mhm.
Yep. That's my question.
By training.
So like by perceptron, are we focusing on a like computerized machine device to simulate the ability to recognize and discriminate, something like that, or is it like other technical meaning applied here?
Yeah. First, by training, we mean an automatic way to adjust the W, the corresponding coefficients on each input variable. So we were talking all the way about training, which means we talk the way to adjust the parameters here. So for what the perceptron represents, it represents a simple classification, binary classification rule we apply to the data. And we all in all the discussion, we use a toy two-dimensional data to visualize the idea. But if you remember the question mark right here, we are not limited to two-dimensional data. If, for example, you have an image of maybe 16 by 16, and then each one pixel of your image will correspond to a number. Let's say it is a black-white image. It will correspond to a number. Then you will have 256 numbers, right? The 256 numbers corresponding to, okay, this is one direction. This is two direction. This is the third direction. And if you can imagine, you can have more directions. Of course, we cannot visualize in three-dimensional in the picture. You have this 256 directions to put your data point in. Each point lives in this bizarre high-dimensional space. And the perception as a high-dimensional creature. Remember this first argument, the number of coefficients equals the number of variables. So it happily lives in the same bizarre high-dimensional space as the X. And all of our argument applies to there as well. Okay,
Okay, so yep.
I hope that,
Sorry, so what is the X apostrophe S again?
sorry?
The one next to the coefficient. Can you scroll down? Yeah, that one's the hashtag X apostrophe S.
Okay, that means when you make the decision about something, you compare the computed A with some threshold.
Not that one's like a little up. Can you move? Yep, that one.
Which one?
I
can
think
you
he
move it?
means the number of W's to the number of X's
Yes,
is going to be equal. Yeah.
Yep, I'm not sure what they are, so I know the
That means
W one
you-
is a
You look, that means you have an X table. You have an, sorry. You have an X table. And this represents an instance, an observation from the real world. And the column means some concept, some attributes describing the X. So what I have drawn above means each of those columns represent a direction in which the particular data sample can change itself. It is you can consider it's a degrees of freedom for the data to vary in a space. And this means for the same number of degrees of freedom, you will have the corresponding W. One for each column, one for each column. So that means the number of W's equals the number of X.
right. Thank you, sir.
Okay. Thank you very much, everybody. Have a nice day and nice weekend. See you next time.
See you, sir.
Bye-bye.
Bye.